to the top of this chat. So without further ado, I'll hand it over to Jiaqi and turn off my mic and my screen.
Okay, well, thank you everyone for joining. I know that we're all really excited to be part of this remote conference. I'm always really excited to be part of Women Who Code. My name is Jiaqi Liu. I had previously been a director in the New York City network for Women Who Code, and I live in Chicago now, and I work with the Chicago network here as well. Today, I want to talk a little bit about coding interviews and coding challenges in particular. I know that coding challenges can feel terrifying sometimes, but I hope that some of the strategies I talk about today will help you feel really confident in tackling coding challenges and that they're not so difficult after all. And I don't know, maybe they can be even a little bit of fun. But I definitely want to preface this by saying, I know that I have failed a ton of coding interviews, so definitely don't ever feel bad if you don't immediately ace them off the bat. I don't know who does that, but you know, over time, I think a lot of practice, a lot of thinking in these kind of patterns and different strategies really help in the long run. And unfortunately, you know, coding interviews are pretty prevalent across the tech industry. So it is a really important skill set. Although, you know, not all companies do them anymore. They're not always the best way to assess skill sets. So there's actually quite a lot of really cool companies that don't do coding whiteboard challenges. So that is also always a thing to think about when you're interviewing whether a company does that or not. So dive straight in. So I'll talk a little bit about, you know, what I mean by thinking in patterns, some of the common patterns that coding problems fall under, and I'll deep dive into three of the common techniques that come up, and those are using, you know, pointers and using a heap as a data structure, and then last but not least, dynamic programming. Cool. So there's many possible coding problems. You will see infinite ways of framing them. Some will have real world examples. Some will just straight up be, can you traverse a graph? So it's kind of impossible to, you know, find all these problems, do them, memorize the solutions. But they do fall into a finite amount of categories. So for instance, you know, graph problems, tree problems are pretty common. String manipulation is really common. So finding, you know, a palindrome, things like that. So it's really key that you are able to identify similar patterns and know when to apply certain techniques. I'll talk a little bit more about the different techniques, but sometimes you'll run into, you know, maybe a complicated problem where you'll have to apply several techniques to get to a solution. So maybe you want to sort the data structure first and then apply one of the following techniques around, I don't know, using a pointer. But again, these techniques, they are layered and they help you find the optimal solution. So not just, you know, a solution, but one of the higher performing solutions. So yeah, you want to be able to recognize the pattern and figure out what technique to approach it with. And this can be really, really challenging, but once you figure out the right technique to apply to a problem, you kind of, you know, unlock the ability to solve that problem. And if you're not approaching it with the right technique, then, you know, you're stuck. And sometimes these coding interviews can go by really quickly. So you'll need to be able to very quickly recognize the pattern and figure out how to apply the appropriate technique so that you can get right into, you know, coding and diving into it. So some of the common, you know, techniques that, you know, I am going to be talking about using pointers today. I'm going to talk about the priority queue, or manipulating a you know, key variable to store and max heap, min heap, and then also a little bit about dynamic programming. But there's a ton of other techniques like backtracing, using some sort of stack to manipulate data. Using a hash map, if you have to be able to fetch data in constant time and look up key value pairs. Using a tree with an IE instead of a tree with TREE. So a tree with an IE will allow you to do any kind of string searches. So if you're being asked, how do you implement autocomplete? Something that you might want to think about is creating a tree structure, having a dictionary in the tree structure so that you can traverse through it. Breadth first search and depth first search. Rarely will anyone straight up ask you to implement one of them, but what they will ask you is a problem that requires you to know how to implement breadth first search or depth first search in order to truly solve it. So that's something that you will want to pay attention to is, identify what kind of problems will require you to know these kind of implementations and apply that implementation when you run into it. Okay, so I'm going to dive straight into the pointers technique. So what kind of problems do you use this to solve? So if your input is a sorted array, list, or matrix, basically anything that's sort of sorted and you know what the relationship between the value and the value after it is, you can use a pointer to traverse through the data structure while comparing elements of the list. This will save on space because you don't have to make a copy of the array. You're just using a pointer to traverse through it. And it usually saves on a level of iteration too, because by keeping a pointer on where you are most interested in the data, you can avoid using nested loops, which tend to lead to higher complexity. So how do you use it? So you will use one or more pointers to keep track of location as you iterate through the list or matrix. And this is, the value that you're most interested in. And then you have some conditional logic that will tell you when to move the pointer. So I'll go through an example problem. Okay, so a common problem that uses this technique is if you're given a sorted array of integers and you want to find the target sum. So you need to write a function that takes the array of integers as input and then the target sum t. So find the location of indices of the two numbers that add up to the target sum. So you could do this the brute force way by, iterating through the array twice, and then you'll check every integer against each other to see if they add up to the target sum t. But this will cost you O of n squared, which is not the most optimal solution. And usually in these interviews, you have to get to the optimal solution or the near optimal solution in order to consider it as a pass. So the pointer solution is you know the array is sorted. So you know that the smallest numbers are at the beginning and the lowest numbers, the highest numbers are at the end. So you can keep two pointers, one starting from the beginning and the other starting at the end, and increment the pointer depending on, if your calculated sum is less than or smaller than the target sum. So I will go through an example here. So in this example, let's say you are given the array 2, 5, 6, 7, 9. You'll notice it's sorted, and then the target sum is 8. So you'll keep a pointer at index of 0, which is the 2, and then you'll keep another pointer at the very end, which is the number 9. So you calculate the sum of those two numbers, and the sum is 11, which is higher than the target sum that you're looking for. So what you do is, because it's higher, if you move pointer 1, you're going to get a bigger number. You know that because it's sorted. So you're just going to get an even bigger sum, which moves you further away from the target sum. So you have to move pointer 2, because if you move pointer 2, you'll be pointing at a smaller number closer to the front of the array. So you move pointer 2 to index sub 3, which is 7. And then you calculate the sum between pointer 2 and pointer 1 again. This time you get 9. It is still higher than the target sum. Oops, I don't know what happened. It is still higher than the target sum. So you have to move pointer 2 again to an even smaller number. And once you move that, you get 8, which is the target sum. Hooray, you're done. The response here is actually going to be index sub 0 and index sub 2, and you're complete with this problem. If you had, let's say, your target sum was 15, then you would probably exit out because there's no, actually, no, then you would want to move pointer 1 over to the 5. But I think that it isn't a sum that exists here. So you would traverse the whole thing and then realize that, this isn't a target sum that I can meet with this array and exit out. Oh, actually 6 plus 9 is 15. Okay. If your target sum was 15, you would just move pointer 1 until you get to that sum. If your target sum does not exist within the array, you would probably exit out and return null or something. Cool. So that's the 2-pointer approach, and by doing that, you only have to iterate through the array. At most, you only have to iterate through the array once, and at most, your big O is big O of n. So note here that if you do not have an array that's sorted, if someone just gives you a random array and say, fine, the the target sum for this array or the location, I guess you can technically, finding the location, the array has to stay intact. So you know where the original location is, but you can sort of play around with if an array isn't sorted, what do you do? And how can you still leverage the pointers? All right, common ways that you'll have to use this technique. If you are presented with a problem that says find a pair among this, matrix or this list, the best way to do that is going to be using, a pair of pointers to find whatever the criteria is instead of iterating through it of n squared time. And then binary search, technically the problem I presented to you is an interpretation of binary search because, you want to be slicing it in half every time. Any kind of matrix operations, I mentioned that this is this pointer approach is relevant to matrices, which are 2D arrays and arrays itself. But of course, it's a little bit more complicated. But in a matrix operation, you would just store the pointer as the 2D locations instead of just the index. And then there's a very similar technique called the sliding window approach for slightly more complicated algorithms that also, reference something where you have to traverse a list or matrix and you have to look at more than one element at a time, but you don't want to have to iterate through it in a nested structure. This has a link to a webpage about the sliding window technique if you're interested. Yes, sorting an unsorted array will increase complexity. So sorting is n log n, but a solution that is n log n is always better than a solution that's n squared. So sorting and then iterating is still better than using a nested loop. So the next technique that I'm going to touch on is the priority queue or heap approach. So I have a link in the heap about the max heap and min heap implementation, and more about the data structure. A little bit about this. So a max heap will always in the root node have the maximum value of that heap, and its children is either, on one side or another is also maintaining a specific structure. And then min heap always in the root has the minimum value in the heap. This becomes important because you use the priority queue or max heap, min heap approach when you're asked to find, the maximum within a data structure, the minimum within a data structure, the closest k amount of points in a 2D plane, the topmost elements within a array. And the reason why you would want to use a heap is if you're asked to find, the top k maximum numbers in an array, you might want to store a heap of the size k to be able to get that information very easily. So how do you use it? Like I said, if you're asked to find the top k number of elements out of an array of n elements, you store k elements in a heap or a priority queue and iterate through the n elements and update the heap and priority queue as you go. In a variation is if you are asked to only find one maximum or minimum, then you don't need to have to be too concerned about using a heap or a priority queue as a data structure, because you can then use a single variable to store the current maximum, the current minimum. Why do you use this? All of this is to save on time. Again, you don't need to iterate through the array or matrix as many times, but you are adding an additional complexity factor by having to store, additional data. So there's a space complexity that's being added here. I will go over a very common example. So let's say you're given an array and an integer k. You are to write a function that will find the k smallest elements in the array, given those two parameters. The brute force solution is to sort the array. I think someone pointed out earlier that sorting is still pretty costly. And then grab the kth element, I guess, or the first k elements. This will cost us O n log n, plus I guess grabbing the kth element, because the cheapest way to sort is n log n. There's different sorting algorithms will have different runtime complexity, but for the purposes of coding interviews, it's always safe to assume that you're using the most efficient sorting algorithm. The max heap algorithm is that you would store the k elements in the max heap, and as you iterate through the array, you'll update the max heap and inserting or removing the element if they're smaller or larger than the root of the max heap. So the thing that you have to know about heaps here is that when you insert or remove an item from the heap, you have to sort of rearrange the heap so that it has the structure where the maximum value, or for max heap, a maximum value is at the root. And this rearranging of the heap still costs, it means you have to traverse through the size of the heap. If you're storing k elements, that is still going to cost log k. So the structure, it's an optimization, but it's a small optimization, but it does lead to a better implementation, and it's big O n log k, assuming k is always smaller than n, since k is a subset of n. Okay, so I have an example of the implementation here in Python that I can sort of walk through. So you would first need to create a heap and add the first k elements to it from the array. At this point, you don't really, care because you just want to populate the heap. And the way that the heap is structured, the maximum value out of the first k elements will be at the root of the heap. Note here that I used a library from a built-in library in Python for the heap implementation, but in some coding interviews, you will be asked to basically implement the functions for pushing to the heap yourself. And that is something that can be very tricky to do if you haven't practiced it already. So part of knowing how to use this technique also involves knowing how to implement the logic for what to do to reshuffle the heap so that when you push, the root still remains the maximum or minimum, depending on what kind of heap you're using. All right, so you create the heap, you add the first k elements to it. So you push all of those. Now you have a heap where there's k elements and its root is the maximum of those k. And then you iterate through the rest of the list. And if the item in the list is less than the maximum value in the heap, you remove it from the heap. There's now a higher maximum value, or actually less than the root of the max heap. Remove it from the root and update it in the heap with the new item. So in this sense, this heap is always going to contain the smallest numbers out of the input because you're always kicking out the largest values in the heap and replacing with something else. And this would be sort of the implementation. All right, common problems where you want to use max heap or min heap is, if you need to know, for instance, the k maximum occurring words in the set, this actually ends up being a very similar problem to what we just went through. And you would instead, your input would just be word and a mapping of the word and the count of the words. So you have to manipulate a dictionary instead of a list. If you have to merge sorted lists or sorted linked lists, a max heap or min heap can be really useful. And then if you're given the tournament tree problem, which is given n players, how many games do you need to play to find the second best or k best player? So these are kind of the common set of problems. It's a little bit more data structure oriented than the pointers example, and it does involve knowing a little bit and feeling comfortable with working with max heaps and min heaps. So I recommend, if you do want to learn more about this, to check out the article that I had linked in the heap link on the page for that. Okay, so the last thing that I definitely want to talk about, but I won't have time to dive into it as much in this presentation, is dynamic programming. Dynamic programming sounds really scary to a lot of people, but at a very high level, it's very much about, if you're working with a problem that could be solved with recursion, how can you cache or store any of the previously calculated items so that you don't have to make any repeat calculations? When do you use recursion? So any problems you have that involves optimization. So if you're being asked to optimize on profit, optimize on space, things like that, you'll probably end up having to use dynamic programming, because a lot of those optimization problems require you to calculate a lot of the different permutations that could happen and then select the permutation that is most optimal. So a lot of those kind of problems center around dynamic programming. Problems that if you think about and, your first thought is, oh, this sounds like something that could be done with recursion. Problems that otherwise could be solved with recursion, they tend to perform better or just be a more straightforward, easier to understand approach with dynamic programming. And by recursion, I also put in parentheses, that's something that contains a subproblem. You solve a recursive problem by solving, some of its other subproblems and then knitting them together. very conscious of this. We already sort of touched on it, but dynamic programming is trading time complexity for space complexity. So you're going to save on time because it'll be, faster to iterate through, but you're going to create a lot of space complexity because in order to speed things up, you're caching all that information. So you're creating a lot of different data structures potentially to store previous calculated calls so that you can reference them very easily, but that trades off on space. And this trade-off on space and time complexity is something that if you're doing coding interviews, you should feel very comfortable talking about. And it's something that interviewers definitely look to see that you have an understanding of. Typically for dynamic programming, you take the recursive approach. So you do have to sort of be able to identify what a recursive approach will look like, find what calls are being repeated, and then caching them so that you are only calculating one subproblem once. I'm going to talk about the Fibonacci approach because this should be something that is pretty common and familiar and very, you can see the code fits nicely on my screen. But the recursive approach for Fibonacci is, if you, first of all, Fibonacci, you are trying to find the nth number in the Fibonacci sequence. And in the Fibonacci sequence, you're adding, the previous number with the one before it. And if it's the very beginning, if it starts with 0, it's going to return 0 because there's nothing in front of 0. If you're at 1, it's also going to return 1. And then subsequently, you have another iteration of 1 because the third Fibonacci number is still 1 because it's 0 plus 1 equals 1. The next one is 1 plus 1 equals 2. The next one is 1 plus 2 equals 3, etc. So the recursive solution is to just, take the previous Fibonacci number, add it to the one before that. If it's 0 or 1, which are sort of like base positions, you just return 0 or 1. The more optimal solution, which can be done in O of n time, is this solution where you are now caching the Fibonacci n sub n minus 1 and Fibonacci n minus 2 as A and B. And this way, you're always sort of caching what the two numbers in front of the current one is. So as you calculate it, you're able to retrieve that, calculate it only once, and this puts you in a position where it's O of n. And this is sort of the essence of dynamic programming, is that you want to kind of avoid recalculating things that you could have cached or stored from a previous calculation. Okay. Again, as I mentioned, I don't really have time in this talk to dive super deep into dynamic programming, but one of the most well-known computer science programs that require dynamic programming as a solution is known as the Knapsack Program. This links to the Wikipedia page about it. Specifically, there is, I guess, a notion called the O1 Knapsack problem, where given a set of items, you have that has weight and a value, you're also given a constraint on how much weight you can put in your knapsack. You have to find what the optimal items are to put in your knapsack such that it fits under the weight constraint, but you are trying to optimize for the most value. And then specifically in the O1 knapsack program, you can either take or leave an item. You can't have, half an item. This is the example from the Grokking Dynamic Programming Patterns for Coding Interviews on educative.io. But let's say, you have apple, orange, banana, and melon, and its weights and profits are listed in, two different arrays. And you want to be able to identify, which items can you take that will maximize profit and fit into your knapsack, which has a capacity of 5 being the weight. And the answer here is the actually the banana and the melon gives you the most optimal profit for the weight that you are constrained on. They add up to a weight of 5 and they add up to a profit of 10. The way that you solve this is you need to, calculate the different combinations possible that meets that are under the weight limit. And then from those, pick the one that has the maximum profit, which sounds straightforward, but it involves calculating out different permutations, storing them in a data structure, and using that to build off calculating other permutations. Like I said, sadly, I don't have time to dive into this. I definitely recommend you, reading up on it if you're interested in trying to code it yourself. Common problems that require dynamic programming, like I said, the O1 knapsack problem is quite common. The Towers of Hanoi problem is another well-known computer science problem. Anywhere where you're asking to get a subset of a set, which the knapsack problem is actually identify a subset of this set of items given these constraints. And anywhere where you're asked to compute any kind of permutations, so compute the permutations of this list of strings, and that can be a list of unique strings or this not unique. And also a very common, I guess, computer science-y problem is sometimes you're asked in these to, given a string of different parentheses, open brackets, close brackets, check if that is a string of valid parentheses, which means that all open parens have a corresponding closed parens. So those are sort of common problems you would solve with dynamic programming. Okay. I want to end with some general themes I touched on, but also emphasize them. A lot of the techniques around coding problems focus on figuring out what is the least amount of information you can store in memory to avoid recomputing something or revisiting an item in the input such that you can calculate whatever, desired solution you're calculating for. So in the pointer solution, you just need to know 2 locations and when to move those pointers. In a max heap, you just need to keep the top k, smallest values from the array in the max heap. And in dynamic programming, you just need to keep the permutations that will help you find a way to optimize for profit. So a lot of this is finding out what the minimal amount of information you can store and reference is to solve the problem. And then that also touches on you are always, trading space for time in those. That most ideal solutions will mean that you don't have to store extra variables and you can do an O of n time. That's with the 2 pointers approach. But ultimately, that's not always going to happen. You have to be able to talk about the trade-offs you're making with, I'm storing a lot, I'm caching a lot of information, but it's worth it because it's going to make this algorithm a lot faster, run in O of n time. And this broader technique kind of plays into a lot of different problems as well. All right. As I mentioned, I didn't have enough time to dive deep into dynamic programming. So I have some resources for that. And a lot of the things I've talked about, a lot of the other patterns that I didn't have a chance to talk about are also in this Grokking the Coding Interview Patterns course. All right, that is it from me.
Awesome. Thank you so much, Jiaqi. This was a phenomenal talk. I think we are about at time, but if folks are interested, they feel free to reach out to Jiaqi and make your way to either the session lobby or check out our networking opportunities where you can go meet up with other wonderful participants. Thank you again, Jiaqi, and everyone have a phenomenal rest of their Women Who Code Connect Digital experience.
All right. Thank you, everyone.